There's a few familiar faces in the audience, but I will cover the basics so everybody knows the business that we're in. We specialize in the rapid discovery of new materials, in particular for energy and electronics applications. And our business model is that we interact with large multinational OEMs, like the ones that we list here, who form our channel to market. So they integrate our materials into the devices and products that they then sell to their customers. Actually, it was quite a varied list of OEMs that you saw there, ranging from the aerospace industry through to the electronics industry. You may ask, what have they got in common? Well, actually, most of them are facing the same common drivers in their businesses. They're trying to increase the return on investment that they make on research and development. And materials development is perhaps one of the most difficult challenges that many of these companies face. And so they come to us to access state-of-the-art technology that can accelerate timelines and reduce the technical and business risks that they face. Part of this is the access that they've got to the high throughput platform that we've got at our facility in Southampton. And I would encourage all of you to consider attending our next Investor Open Day. We had one earlier this year that a few of you came down to see. We have this platform that allows us to make hundreds of systematically varying materials with different compositions on a single substrate using an automated process. And that basically allows us to compress the work of what can be decades into a few months and make sure that we get results that can identify promising new materials as rapidly as possible. One of the longest relationships that the company has is with Toyota. I'm pleased to say that as far as we know, they haven't installed any interesting software in their diesel cars. They came to us with another recurring nightmare, and that was that their hybrid vehicles, like the Prius, some of you may own a Prius or have at least driven one, that one of those Priuses with a lithium-ion battery in might go bang at some point when driving down the M3. Because as you know, lithium-ion batteries, they're actually pretty powerful these days. But the problem is that they have got an inflammable material in them. And very occasionally some consumer electronics catches fire. In fact, of course, we were all entertained with the lurid headlines of the Dreamliner's launch and the problems that the lithium-ion batteries caused on board there. And Toyota, and in fact, they're not dissimilar to any other automotive company, really don't want a mass recall of their vehicles. So they came to us and they said, okay, what we'd like to do is develop a non-flammable lithium-ion battery. So we want you to try and work with us to take out the liquid electrolyte, which is the flammable component, and replace it with a solid ceramic that can form the same function, i.e. allow lithium ions to move from one side of the battery to the other, and give us the same benefits that we are enjoying with our hybrid vehicles. So we set to work, and in fact since then we've filed about 9 patents together with them, so it's been a very fruitful collaboration, and it's resulted in us being able to make batteries with a series of pretty interesting properties. Not only are they non-flammable, but also they can charge much more rapidly than a standard lithium-ion battery, so about 6 times faster. So in the context of your mobile phone, that means that you could charge the battery from empty in about 10 minutes instead of an hour. And of course mobile devices are supposed to be portable rather than being plugged into the wall for vast tracts of the working day. So this is quite appealing for some market sectors. Also, they're very good at retaining charge. So even if you don't use your phone, for instance, you put it down, the battery will drain because standard lithium-ion batteries have got an intrinsic leakage current, which means that actually they self-discharge. But solid-state batteries don't quite have the same problem. And also they're much smaller, so they're about half the size of a standard lithium-ion battery. Great stuff. And actually what we said to Toyota was, well, we're really quite interested in some of the other markets that we could address with this technology that are outside of automotive. And first of all, what we wanted to do was just make sure that we hadn't reinvented a wheel. Because actually we didn't invent solid-state batteries. They were previously invented in the 1980s by one of the US national labs, Oak Ridge National Lab in Colorado. And here's a little cartoon that explains the differences. On the left-hand side, you see a standard solid-state lithium-ion battery using lithium cobalt oxide, which is in fact the cathode materials that are in your lithium-ion batteries in your mobile phones at the moment. But instead of having a liquid electrolyte, they have something called lipon, which is a lithium phosphorus oxynitride material, which is a complex ceramic that is conductive for lithium ions. And then they have a lithium anode, which gives them quite a high voltage, quite a high operating voltage. Now, they actually work quite well, but the problem is that you can only make them in a pretty thin stack. You can only make a thin layer of each one of these components in the battery, and then you have to encapsulate the whole cell. And if you want a greater capacity, you've got to stack these different cells on top of each other in the same way that you'd put batteries in a torch. So that's actually pretty energy inefficient in terms of the amount of energy you get for a certain volume, because there's a lot of volume taken up by the polymer encapsulation and the substrate on which these materials are deposited. So our innovation is shown on the right-hand side, where we can actually put multiple layers of these different cells, one on top of each other, because we have a low temperature formation process which allows the previous layers to stay intact as we form the subsequent batteries on top of the initial ones. And that means we can make larger batteries, which actually start to become quite useful for some of these applications. So where are we with patents? We've had some interesting news over the summer. The top two were the first two patents. We filed both of those together with Toyota. They were published and indeed granted, firstly in the US and then secondly in Europe. And then we've had three more quite broad patents which were filed later, published in the summer. And that's allowed us to start to talk about the technology a bit more broadly at scientific and trade conferences. So you will see some of our scientists and business development people starting to appear at the usual battery forums, talking about the technology and spreading the word. So what's our roadmap look like? We can take you from left to right, going across the scale here, starting with relatively small batteries, what we call micro batteries, which are actually useful for Internet of Things applications. And these are really autonomous wireless sensor network applications. I'm going to talk about this in a bit more detail, which really is one of the most rapidly growing sectors at the moment for technologies, not only to provide power but also sensor devices associated with them. Then there's wearables. I'm sure some of you own some of these interesting devices. What's usually quite infuriating about them is that you generally have to recharge them every evening when you want to download the number of steps that you've walked that day. Then we've got, of course, consumer electronics. That's the largest market out there at the moment, but that's rather cutthroat. You need to be able to hit a pretty aggressive price point for that. So we'll come to that one later. We're actually focusing on some of these earlier markets which have, let's say, more favorable gross margins that you can achieve. Then, of course, we get to the goal that Toyota is chasing with transport, with hybrid vehicles and electric vehicles. They're much larger batteries. Typically for an electric vehicle, you need 100 amp hours of energy storage, which is quite a chunk. And then finally, of course, it'd be very interesting if you could combine these solid-state batteries with photovoltaic panels so that you can store energy from these panels locally on the roof of your house without having to have a separate power wall which is Elon Musk's vision of how he might use some of the batteries that are coming out of his gigafactory. But the interesting thing about our technology is that actually you make these cells using the same basic process that you use to make PV panels. So intrinsically, you could imagine a factory being able to make these devices in an integrated manufacturing process. So most of the sensors for wireless sensor networks are MEMS devices. This is a diagram which is often shown by Bosch in their presentations. It shows how sensors started out in automotive, then moved through into consumer electronics, typically games, and then finally have become very popular in smart homes and smart buildings, which is the most rapidly growing sector at the moment. This is what they look like. You have a building where you're trying to control temperature and light and humidity, often using HVAC systems, so heating, ventilation and air conditioning systems. And the idea is that you have an autonomous system that you put in that doesn't need to be cabled, because you have a lot of existing HVAC systems that actually were put in quite some time ago, and you can make them much more efficient by having little devices that you install in the rooms and send back enhanced information through to a central control system. The second sector is automotive. Those of you who have bought a new car in the last couple of years will be astonished by the vast array of electronics that you have purchased along with what you thought was merely a vehicle to get you to work in the morning. In fact, the amount of electronics has increased to the point where the cable loom is the third heaviest component in the vehicle, so behind the chassis and the engine. And of course, the manufacturers are looking for ways to strip out the cost. There's an awful lot of copper associated with that, as well as the weight, so that you get a reasonable fuel economy out of the vehicle. And the same can also be said of aeroplanes. There's a huge amount of instrumentation goes into modern aircraft, and there's a big demand for reducing that weight for obvious reasons. And then perhaps one of the most interesting and, exciting innovations that we've come across recently has been the Google Lens. You can look this up. This is actually explicitly mentioned in the Alphabet reorganization that was announced in August. This is actually for measuring the level of glucose in tears of diabetic patients. And it's a semi-disposable lens, and it actually has a small PV panel. It has a little battery, and it has a sensor and a transmitter, so that instead of having to take small blood samples, you can actually just get all of the data you need from this lens. And in fact, Novartis has taken a license from Google X to commercialize this. They've realized that the market is vast, and this is a device which is in prototype development at the moment, using the types of batteries that Ilika is making. So most of these devices actually would have been science fiction just a few years ago. And what's really happened is that the power budget for the electronics has decreased rapidly, and the efficiency with which you can harvest energy has increased. So you're getting much more efficient photovoltaic cells. You're getting actually energy harvesters that pick up vibration that can recharge these batteries very efficiently. And so when you're getting this nexus point, you're able to come up with devices that actually function. And these are the different components. You've got your sensor, got a little power management circuit and a control unit, energy storage, i.e. a battery. You've got your transmitter. Ideally, that is over a low energy wireless network like LE Bluetooth or Zigbee. And you've got your harvester, often a little PV panel. So what are the choices that the designer has got? You can use conventional batteries. The obvious downside of those is that most of them are actually primary batteries, which means they have to be replaced. So imagine you're a homeowner and you've put 100 sensors into your house to make sure that your heating and air conditioning system works nicely, and then every year you've got to go around and change them all. Well, that's not going to be very popular. So that's why you haven't really seen a significant rollout of those types of devices broadly. Then you've got supercapacitors. Now, you hear a lot about supercapacitors. They have improved over the years, but the problem is they're not very good at storing energy. They're very good at giving a pulse of energy, but if you want to store energy that's harvested gradually over a long period of time, they don't retain that charge. And that's why solid-state batteries are very attractive, because they have a pulse discharge capability, but they're also very good at holding charge. So, where are we with our development? We've actually got a pilot line that we got up and running. We finished the factory acceptance test in September of last year. We actually managed to bring Greg Clark, MP, down to open it. There's a picture of him. He's the good-looking chap on the far left, in case, sorry, on the far right, in case you don't recognise him. Oh dear, Freudian slip. And this is allowing us to make solid-state batteries on a large wafer, like you see there. There's an engineering diagram of it. And we're currently making sure that the performance of these batteries is exactly what we need for the applications that we were looking at, talking to some of the companies that are interested in these sectors, and making sure that our roadmap matches their roadmap. There's a picture of one of the first batches that came rolling off this pilot line. We sliced this up. You can see the little bunny ear contacts that we use to connect these batteries into the electronic systems that they're targeted at. And in terms of what the rest of the year and into next calendar year holds for us, we are actually using these batteries to secure proof of concept programs with the OEMs that we're dealing with, and using that as a springboard actually for commercial activities and the licensing of this technology into the mass market. It's not on my slide, but also an interesting milestone or signpost for that is the recent appointment of Mike Ingalls to our board. Pending a successful shareholder vote on Wednesday next week, he'll be taking over as chairman. And Mike was the commercial director at ARM Holdings for many years and propelled them to the growth that many shareholders have enjoyed in recent years. And he saw our technology, was very enthusiastic about it, and agreed to join our board to help us move through this next phase of commercialization.